So, the focus on energy needed to drive electric vehicles has recently shifted from fossil fuels to electricity. And then in the next years, it is estimated that the use of electric vehicles will increase very sharply as compared to fossil fuels. But the issue with electric vehicles is the charging system. It has been a problem that needs to be resolved. So I am Daniel Free and I will be presenting on electric vehicle chargers with minimum current ripples using at least 3 toroidal inductors. And then this is the outline of the presentation. I'll talk about the intro, which is the system requirements, scope of projects, the software implementation, as well as the experimental results. Now, the problem statement is that the electric vehicle industries face difficulty with manufacturing of an efficient and reliable charger for electric vehicles. This includes the slow chargers as well as the requirements needed to frequently charge these vehicles. So the charger needed or the charger being proposed is able to charge electric scooters as well as golf carts and electric vehicles. This is the proposed topology, the equivalent circuits. The front end is an AC to DC converter, which is made up of 4 diodes, followed by a coupled inductor, and it is having 3 legs. This coupled inductor is connected to an edge bridge rectifier. So this edge bridge in our proposed topology, the first 2 switches, which is switch S2 and S3, will remain off throughout the operation, and they will stay off because we need their body diodes to conduct. We also have our output capacitor and then the batteries here. So now I'll walk us through the operational waveforms. We have 2 waveforms depending on the operation, whether we have a a duty cycle less than or greater than 0.5. So on my left over here is the duty cycle, which is less than 0.5. When the duty cycle is less than 0.5, we have the gate to source voltages of switch S5 and X6 alternating. And then we can see that the the inductor current passing through the leg C and B, leg A and B, is equivalent to the overall inductor current passing through I, which is the IC, passing through the first leg. When you go to the other side as well, which is when the duty cycle is greater than 0.5, you can see that the gate to source voltages for switch S5 and X6, they have a very wide duty cycle, and then it is similar to the duty cycle when it is less than 0.5. Between the I5, between the IB and the IC, we get a resultant of IC over there. Yeah. Now, this is the steady state analysis of the proposed charger. We have 4 different modes: mode 1, mode 2, mode 3, mode 4, moving from my left to my right. So we have the switching sequence to be mode 1, mode 2, mode 3, mode 2, and then mode 3 when the duty cycle is less than 0.5. And then we also have mode 2, mode 3, mode 4, and then mode 3 when the duty cycle is greater than 0.5. So this is the steady state analysis, the equations for each of the modes. For example, we have for mode 1 the voltage across the inductor, coupled inductor leg 1, is -2/3 multiplying the expression half of output voltage minus input voltage. And for example, if we take mode 3, the voltage across inductor leg 2 is the same as inductor voltage across inductor leg 3, and it is given by negative voltage input voltage plus output voltage, all divided by 3. Now I'm walking us through some of the procedures we took to build this reliable and efficient charger. So practically we use the DSP board, and then for the battery charging we need to take some voltage readings and then also current reading from the battery, and then that one is used for PID control. So apparently, what we did, so we needed an ADC reading, using the ADC reading to read, and then to reduce the noise we use filtering capacitor as well as shielded cable, and then also shorter cables. Yeah, this is the experimental setup. Over here we have the DSP board, we have the inverter leg, we have the current probes to measure the output currents, and then we also have the voltage probe to measure the output currents. These output currents and input currents are sensed with a reference. So the output current is being sensed with a voltage reference of 28 volts, with a voltage reference of 200 volts. This 200 volts is being compared to the output voltage, and then the output voltage is passed through a PI controller. This PI controller, the output of this PI controller becomes the current reference, and then this current reference is being compared to the measured current from the battery, and then this is also sent to another PI controller to compensate for the error and then do the correction. So this is how the control circuits works in the proposed topology. Now this is the experimental results. On my top left is the output voltage, which is the 200 volts, and then we have our input voltage from the mains, the peak to peak, so the peak voltage, so we are getting 155, and then the input current is around 9 amps. So we also have the gate to source voltages of switches S5 and X6, and as I said, these they switch complementary. This, so the figure in the middle, the top middle, is the zoom in version of the gate to source voltages of switch S5 and then S6, and then over here the far left down figure is the zoom out version. We also have the inductor currents being displayed over here. So the zoom out inductor current is the one on top, my top right. This one, because it's a coupled inductor, the inductor is a coupled inductor, we can see over here it doesn't discharge directly straight to the bottom, but there is a bit slow discharging and then slow charging at the very top over here. The coupled inductor, the effect of the coupled inductor is the reduction in the current ripple. So we can see in the black waveform the current ripple has really reduced, getting around 0.2 amps, but for the other two legs, which is the green and the red, we are getting around 1.2 amps each. So the proposed topology really reduces the input current ripples associated with the inductor. And then over here in the middle down figure, we can see the zoom in version of the current ripples. The figure down on my far right down there is the THD. So we did the total harmonic distortion graph, and we vary the input voltage and then the output, we vary the output power to measure the how distorted the waveform, input current waveform is, and then this is the results that we had. The result shows that the proposed topology is very good in terms of the power. As the power increases, you can see that the THD also reduces, and we are having a very high power, which is very which is an advantage of the proposed topology. Okay, so the proposed EV charger presented gives a promising solution to the efficiency and reliability issues that are associated with the conventional EV chargers. This one is having special features of using two boost converters in parallel, and then it shows that current ripples can be reduced to the barest minimum. Ladies and gentlemen, this has been a presentation on electric vehicle charger with minimum current ripples using at least 3 toroidal inductors. Thank you.